Hi, my name is Bill McPherson. These are my teammates, Simpson, Garrett, Rockwell, and Becklo. We are a firefighter team.
So the problem that we had was to build a robot that would navigate through a maze with different type of rooms that are outlined by reflective tape. The robot would have to go into this maze, try to find a baby that is in this cradle, rescue the baby, bring it to a designated safe zone. Then it would have to go back, try to locate a flame, and put the flame out. We also had to qualify the robot within a set of rules given to us by Trinity College. It was part of a competition for the college that they run every year. The boxes up there are actually the size we had to keep our robot within. So it was a 12 by 12 box, and then it can only be about 10.5 inches high.
While our main project was to construct the firefighting robot, our auxiliary goal was to actually build a test arena for this robot to run in through. That way we could demo it for ourselves, find any true bugs that would be showstoppers at the competition, and work them out in our coding as we went along. By doing this, we were able to account for color variations in our environment, account for any ambient, unpredictable lights, such as camera flashes or a wonky ballast in the ceiling. Also, loud ambient noise, because apparently the Trinity College audience is very loud at these events. Another thing that they mentioned was to specifically avoid magnetic navigation systems, as their floors often contain rebar, and this will create magnetic anomalies in the floors, thus providing unreliable results.
Okay, so this is our system diagram. I'm just going to go through the basic parts here before I explain the lines made. We have 3 micros there, micro 2, micro 3 that's an at-mega board, basically an Arduino, that actually runs the motors you see here. This is the parent micro right here, and these lines represent which micro is running which units. This one, like I said, is the parent one and passes serial data here to this micro, which controls the motors and what it does, etc. This is the baby lift mechanism right here, and this is the line scan camera mounted on the servo, and these are the infrared motors. So, this micro controls the infrared flame sensor, and these are the ultrasonic sensors. The first one is mounted on a servo, and for future reference, we're calling these the servo distance, and the ones that are mounted the fixed distance.
We originally decided to buy a drive system for our robot. We bought one that was called Hercules. It included a simple frame, a battery, the wheels, motors, and a motor controller to help control the motor since they were only DC. They were only able to go on and off. We did this at the time because we believed it was best for considering the options for time and everything, that we didn't really have the time to build a full robot from scratch. Since the Hercules robot is actually on the smaller end, we had to design frames to make them bigger. At first, we made these frames out of acrylic, and they actually broke when we were trying to mount some stuff on it, so we decided to go to aluminum. We cut the aluminum out on a water jet system down here in the lab, down here in the mechanical labs at school.
Oh, yeah, that's so much better. Okay, so this is our flow chart for the navigation system. Flow chart is like a graphical representation of code. So just to explain that, and these little quotation marks down here are, these are the commands that are being sent for whatever action. And for a flow chart, anything in a square is an action, anything in a diamond is like a question or something it's looking at to decide what to do. So up here in the top box, the power obviously is turned on. This is state 1, I guess you could call it. And then it moves into basically just a loop with a D-bounce that waits for the fire alarm to go low. And that actuates the robot into rescue mission. And it starts by basically assessing where it is. It can start in a room or it can start in a hallway, and it needs to determine which one's which and where it is and what to do. So basically it gets fixed distances, and the ones that are with the servo painted on the front pointed straight forward with the left and right. And then it uses the servo to turn the ultrasonic on the front to get 110, 90 degrees and straight distances. If the distance right off the bat in the front ultrasonic is 120, which is bigger than the biggest room, it knows it's in a hallway, so it's set to go. It goes right into this stage, I'll explain later, but it is the roaming state. And if it's not, it's on some sort of angle, so it checks to see LA, LB, and LC. They are just the 110, 90 degree distances, and it basically just moves around until those two distances are equal. Once they are, it too goes into this drive straight and into the roaming state. The one in between is exit room state. To just give you the basic idea, it drives to a certain distance off the wall, 10 centimeters right now, takes a right and does that exact same thing. It drives until it's about 10 centimeters from the wall and then looks left for a door. And it sort of creates a situation where it's always looking for a door at the right hand time. It's always going to be on its left. These two right up here are leaving. They'll go to the baby routine and the fine flame routine that put it out. And this, as I mentioned before, is the roaming state. As it is basically a lot of what it does, it's very simple. It just looks for a distance on the right or left greater than 25. And if it sees it, it takes it. Okay, so this is the motor controller software, Micro 3, or that at-mega board I showed you earlier. Okay, this is just the serial function that waits for the command to be sent from the above Arduino. And it waits, if it's not getting sent anything, it just sits there and waits until it does, and make sure the motor's off. And these are the codes that it can send for the various options, increase, decrease speed, forward, reverse. Right positive 10, or right 10, left 10, and that's because that's the angle that the robot can be put on when it's in a room. Turn left 90, turn right 90, those are pretty self-explanatory. These functions right here are the motor command functions for that board. So you have one function that runs all the motors at the same time and basically just makes sure they're all going straight. This one is directional, so you can see there's a 2 and a 1 here, and those are the right motor and the left motor. And in either case, the function, the speed is goes from 0 to 100, and the direction is F for forward, R for reverse. And then, of course, motor set stop is just stop all the motors. Up here is just, these are the IR bumper interrupt functions. They take the variable, the global variable which is right here. You can see it's pretty small. All it does is set that equal to 1. If it is equal to 1 in the main program, then it does this self-correct based on which one it was. Okay, this is the ultrasonic sensor. We use 3 of them right now, maybe more in the future. It's got a 50-degree measuring angle, which basically just means relative to the radius that you're looking out, it will see 15 degrees of that relative arc. It runs off 5 volts, takes about 15 milliamps, and can see, ideally at least, from 4 centimeters to 3 meters. It's a little different in our arena because it's so narrow. But, over here is the Arduino. It's got 40 milliamp source, total source current at 200 milliamps for just the IL pins anyways. The 5-volt regulator is aside from that, so it'll source up to 1 amp, and the 3.3 will source up to 150 milliamps. These two are combined though, so if you get, if you're using this 150 milliamps, that comes out of this 1 amp. And it runs at 16 megahertz. Okay, so these are the other sensors that we use for the navigation. They're both infrared sensors. This one's for the tape sensor. We designed a circuit for this so it would be more applicable to what we wanted. We set the LED current as close to spec as we could get it, 50 milliamps, so it was nice and bright. And we set this optical transistor at its lowest forward current that we could get, so its forward voltage would be as low as possible when it triggers. This is what we were able to get off that. 5 volts obviously is just sitting here when the transistor's off. And once it's saturated, it goes down to 0.28 volts, which is more than enough to get a logic level 0. These are the infrared bumpers. They're adjustable sort of in a similar fashion if that was a pot. The range is laughably 2 to 30 centimeters. It wasn't anywhere near that in real life. And it runs from 3.3 to 5 volts, and its main component is a 3M393 comparator. I guess this last line here was, we looked up the specs and the components on it to get some sort of idea of what it was pulling in for current.
So, as previously stated, we're going to need to detect a specific set of patterns in order to find the baby's cradle. And in order to do that, we've decided to use the line scan camera. It's got a relativistically short exposure time, very close resolution, which allows us to actually calculate how far away we are from the crib. And it's going to be mounted on a pivot servo so that we can determine if we're looking at a green face or a red or blue checkered pattern. In order to determine how far away we are from the crib, we're going to enter in a known value, which in this case is 6 inches, and that's from the leftmost line to the rightmost green line. And from there, we're able to divide that by however many bits we actually see in the line scan camera being pulled down low. From there, we multiply that by 128 bits, and that will give us our full distance away from the cradle. And using that, we're able to drive it right up next to it, latch on, and save the baby from raging inferno.
So this is our design for the baby tailgate lift. Right here is the robot, and this is the cradle here. As you can see, here's a side view of it. The robot will move forward to the cradle, once it has gotten up to the cradle, the line scan camera will tell it it's close enough. This red latch here will come down and close onto the cradle. It's all automatic. It's taking readings from the line scan, making sure where it's close. It closes. It will then back away and take the baby to a safe location. Here is actual pictures of the baby cradle. As you can see, these are the patterns that we are detecting. This is the robot right here latched onto the cradle at the moment. So for the cradle, we will be using two servos. So they're the same servos, same spec and everything, just on opposite sides because we have two clamps. It will go down to one of the microcontrollers, and then it will transfer into one of the Arduinos. So for the code of the baby lift, we will start by entering the room. We'll look around to see if the baby is anywhere. If it finds the baby, it will then approach the cradle. From there, it will keep approaching until it gets into position, saying, all right, I'm in position. It will then latch the clamps. Once the clamps are latched, it will move the baby out of the room and back into a designated safe location, and then it will continue to go back into searching for a flame. This code that is here on the right is code that is for latching the clamps down onto the cradle. There is two different types of clamps here, the left and right. We have to code them differently because they're actually backwards to each other.
And next, we'll go into the flame detection and extinguishing system. It starts in the center with the Arduino, and it basically just takes the input from all the sensors to know whether or not there's a flame that needs to be put out. The most obvious, the white line sensor lets me know whether or not it's in a room. And then if it is, I use a 5-channel flame sensor to know where the flame is, if it's there. Flame detection indicator LED needs to be there by the competition says it does if there's a flame in the room. And the motor gets powered by 12 volts, which runs through a transistor. This is just a flow chart for the code. Basically, find the room, scan for the fire. If it's there, I need to find it and get within 30 centimeters of the flame. Also mandated by the competition. And once I get close enough, I spray CO2, which is set off by a motor, which I'll show next. And once the fire is gone, I've got to exit the room and go back to the starting location. This is a flame sensor that I chose. I chose it because it's got 5 analog inputs, and with all 5, it can cover more than 120 degrees. I can enter a room and know if it's there without turning the robot, and I know where it is, because there's 5 different inputs. And for the actual activation, I've got the fire extinguisher set up, mounted next to a motor. I made a bracket and put it right next to it with a cam. So when I see the flame, I can turn the motor and it turns the cam and actually sets off the CO2. And that motor is run with a digital output off the Arduino. So it energizes the transistor and sends the 12 volts to the motor.
This is our tone decoder circuit. It's the thing that starts the robot off. I think I mentioned that before. We used a NE567, which is a phase lock loop. So as far as the circuit design goes, these equations over here, R1 and C1 set the center frequency, which was 3.5 kilohertz, that the fire alarm actually sounds. We used basically the 2.4K, 160 ohm, and 51 ohm, which we tested on the bench to be about 2,588 ohms. In practice, they vary quite a bit. fit, so you need to measure them. Down here, C3 just sets the largest no output voltage, so obviously there's a lot of noise going on, but a lot of it gets attenuated. You don't want your circuit being triggered off of a 20 millivolt signal. The microphone down here that goes into the signal in is just a simple amplifier of max 9814. We can get a current spec obviously off of it, so 3.1 to 6 milliamps. And that's it. So the result here was a falling time of 36 microseconds, which is more than enough to trigger a low pulse, especially considering that's all the program's doing in the beginning. And that is the tone detection circuit.
So we have constructed and painted the majority of the testing arena. We still have to create a couple of noisemaker circuits, as well as some infrared and ultraviolet lights, just to throw a couple of rocks into the gears that are our robot, and ensure that it is actually capable and prepared to extinguish fire and save a baby. This is the grand sum of our budget, with the two main costs, or the two main drains on it being the Hercules robot coming in at just under $180, and 3 of the ultrasonic sensors at $45 a piece.
For the team's responsibilities, Bill here had mainly the navigation of the robot to navigate through the maze while also being the team manager. Dylan had the fire detection and the fire extinguishing, so we mainly deal with the flame completely. I personally was dealing mainly more with the baby tailgate, trying to actually figure out a way to pick it up and carry it away, while also dealing with modeling up the robot and getting a bigger frame onto it. Garrett was working on locating the baby so we could get up to it, and also the test arena, with every aspect into building the test arena so we could test the robot before going to a competition.
We'd just like to say thank you to John Kidder, Mr. St. Dennis, Ethan, I'm trying to pronounce his name. Sure. Bob Royce, and LED Dynamics for using the water. Any questions?
So the idea of this is that it operates all by itself.
Yes.
And does it have any feedback, video feedback when you want someone up? It walks in there and does it.
Well, this is just for a little competition, so you can, that's the arena right there, you can actually look down into it. It's not actually built for
Like going into an actual house and actually putting out a flame. Yeah, this is just for a simple little competition. Yeah, proof of concept.
I thought it was pretty good, you might get someone to donate a baby so that
Yep. Any other questions?
So I'm doing in your flame extinguishing thing, you said the fifth was 37 years. You let it happen. Is that just distance sensing or is it detecting the angle? Is there
I
a probe chart when we ship that?
Right, I work with the different channels on the analog flame sensor, so basically I've been just seeing what numbers work out, but when it's about 30 centimeters away, what the analog feedback is. And I keep the center sensor, would be the highest reading to know that it's directly in front of it.
So does the glass and CO2 cover the same areas?
It's fairly focused, but you can be quite a ways off and it's still, the spray is pretty wide spray, so it doesn't have to be directly pointed at it, it has to be pretty close. Couple.
When we see it angled glass, okay?
Probably not.
What kind of time frame are you talking about, navigating it for? What are you hoping to achieve time-wise?
Yeah, 35 minutes is the cutoff, let's say 5 minutes, and it's well done.
How's it going?
On level 3, though, on level 3 it's a bit different, I don't think they have any time frame for that, you finish when you finish, but.
So, on the layout of the frame, I don't know what to call it, like the add-on, whatever it is. Why, these are two levels, right?
Yes.
And why are they shaped?
So this one just goes above the wheels and everything, so we could have this one. This one, the one on your guys' right, or left. I'm dyslexic. So on the left is just on the top. So it sits on the top and everything. It's this one way up here. While this one underneath here had the cutouts, so it could actually sit with the wheels right down, like on the center of the wheels, and have the wheels still be able to have room to spin and everything. While also this is right here where the cradle will go in. These are lifts to help push the cradle up, so I had to have a cutout to have let it go over, bring the cradle and lift it up. And the wheels would go here, 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 and here, and this is for wires so we can get into the actual undercarriage where the Hercules robot is.